Welcome to DAR Tutors for online and home tuition. In this video, we will explore electron configurations, a fundamental concept in IB chemistry higher level. By the end of this session, you should be able to, first, understand how light emission provides evidence for discrete energy levels in atoms. Second, deduce and apply the rules for writing electron configurations. And third, explain the factors that influence ionization energies and use them to deduce electron shells and groups. Our understanding of atomic structure has evolved significantly. A simpler but less accurate model is the Bohr model. The Bohr model represents an atom as a nucleus with electrons orbiting in fixed concentric shells, also known as main energy levels. Each shell corresponds to a specific, discrete amount of energy. While intuitive, this model has limitations and doesn't fully explain the complex behavior of electrons. A more accurate and widely accepted model is based on quantum mechanics. In the quantum mechanical model, the main energy levels are further divided into sublevels, S, P, D, and F, and these sublevels consist of atomic orbitals. An orbital is not a fixed path, but a three-dimensional region of space where there is a high probability of finding an electron. So we move from the idea of electrons orbiting in simple shells to a more detailed picture where they occupy complex regions of space called orbitals, which are grouped into sublevels and then into main energy levels. This hierarchical arrangement of shells, sublevels, and orbitals is key to understanding electron configurations. Before we delve deeper into orbitals, let's understand how we gain evidence for the existence of these discrete energy levels. This comes from the interaction of light with matter. Light, and indeed all electromagnetic radiation, has a dual nature. It can be described as a wave, characterized by its wavelength and frequency. It can also be described as a stream of particles called photons, or tiny packets of energy called quanta. These two models are not contradictory, but complementary, and they are linked by fundamental equations. The first equation, c equals f times lambda, relates the speed of light, c, to its frequency, f, and wavelength, lambda. In a vacuum, c is a constant approximately 3 times 10 to the power of 8 meters per second. The second equation, E equals hf, is Planck's equation. It relates the energy of a photon, E, directly to its frequency, Fh is Planck's constant. This equation demonstrates that higher frequency light has higher energy. By substituting the first equation into the second, we get an alternative form, E equals hc over lambda. This tells us that higher energy photons correspond to shorter wavelengths. In summary, energy is directly proportional to frequency and inversely proportional to wavelength. Let's apply these equations with an example. Suppose the yellow light emitted by a sodium street lamp has a wavelength of 589 nanometers. Our objective is to calculate its frequency, the energy of one photon, and the total energy in 1 mole of these photons. First, we need to convert the wavelength to meters, as Planck's constant is in joule seconds. 1 nanometer is 10 to the power of -9 meters. So, our wavelength lambda is 589 times 10 to the power of -9 meters. To find the frequency, we use the wave equation rearranged, F equals c divided by lambda. Plugging in the values, we get a frequency of approximately 5.09 times 10 to the power of 14 Hertz. Now for the energy of one photon. We use Planck's equation, E equals hf. With our calculated frequency, the energy of a single photon is about 3.37 times 10 to the power of -19 joules. This is an incredibly small amount, as expected for a single quantum. Finally, let's calculate the energy carried by 1 mole of these photons. Remember, 1 mole is Avogadro's number of particles. So we multiply the energy of 1 photon by Avogadro's constant. This gives us approximately 2.03 times 10 to the power of 5 joules per mole, or 203 kilojoules per mole. This is a macroscopic energy value, more comparable to typical chemical bond energies. So how does this relate to electron energy levels? When atoms in a gas or vapor are excited, for instance by heat or high voltage, their electrons absorb energy. This causes them to move to higher energy orbitals, placing the atom in an excited state. This state is unstable. To return to the more stable ground state, the electron must emit the excess energy it absorbed. It does this by falling back to a lower energy level. As it makes this transition, it emits a photon of light whose energy is exactly equal to the energy difference between the two levels. This process gives us the key evidence for discrete energy levels. If electron energies could be any value, we would see a continuous spectrum, like a rainbow. But what we observe for excited atoms is a line emission spectrum. This is a series of narrow, brightly colored lines against a dark background. Each line in this spectrum corresponds to a specific energy transition within the atom. The fact that we only see certain lines proves that only certain discrete energy levels are allowed. It's like a ladder, where you can stand on the rungs, but not in between them. The emission spectrum of hydrogen is especially simple and important because it only has one electron. This allows us to clearly see the different spectral series, each corresponding to transitions to a specific final energy level. Here we see a simplified energy level diagram for hydrogen. Transitions where an electron falls to the first energy level, n equals 1, form the Lyman series, which is in the ultraviolet region. Transitions to the second level, n equals 2, form the Balmer series, which is in the visible region. And transitions to the third level, n equals 3, form the Paschen series, which is in the infrared. Notice two key features of these spectral series. First, the lines within each series get progressively closer together as the initial energy level increases. This is called convergence. Second, the spacing between the energy levels themselves also decreases as you go further from the nucleus. They become more closely spaced at higher energies until they merge into a continuum. This convergence limit, where the lines merge, represents the minimum energy required to completely remove an electron from the atom. This energy is known as the ionization energy. So, by studying the frequency or wavelength of this convergence limit, we can calculate the ionization energy of the atom. Let's perform a calculation to determine the ionization energy using this method. Suppose the convergence limit for the hydrogen emission spectrum occurs at a frequency of 3.27 times 10 to the power of 15 Hertz. Our goal is to calculate the ionization energy for a single atom and for a mole of atoms. Remember, the energy corresponding to the convergence limit is the ionization energy for one atom. First, we use Planck's equation, E equals hf. We plug in the frequency of the convergence limit and Planck's constant. This gives us the ionization energy for one hydrogen atom, approximately 2.1 times 10 to the power of negative 18 joules. Typically, ionization energies are quoted per mole. So, our next step is to convert this value. To get the energy per mole, we multiply the energy per atom by Avogadro's constant. This calculation yields 1.31 million joules per mole, or 1310 kilojoules per mole. This is the first ionization energy of hydrogen, which is the energy required to remove 1 mole of electrons from 1 mole of gaseous hydrogen atoms to form H+ ions. Now let's switch gears to the quantum mechanical model. The maximum number of electrons a main energy level can hold is given by the formula 2n², where n is the principal quantum number. However, this formula is an oversimplification. A more accurate model describes how these main energy levels, or shells, are subdivided into sublevels. There are 4 main types of sublevels: S, P, D, and F. Each of these sublevels has a characteristic shape. The S sublevel contains only one spherical orbital. The P sublevel contains 3 dumbbell-shaped orbitals oriented along the X, Y, and Z axes. The D sublevel contains 5 orbitals with more complex shapes, and the Fe sublevel contains 7 orbitals. These orbitals have a defined energy state, and the number of electrons they can hold is governed by fundamental quantum rules. The filling of these orbitals by electrons is governed by 3 key principles. The first is the Aufbau principle. The Aufbau principle states that orbitals are filled in order of increasing energy. Electrons occupy the lowest available energy levels first. The energy order of sublevels is not always simple. There is an overlap between different shells. For example, the 4s sublevel is lower in energy than the 3d sublevel and therefore fills first. This diagram shows the order of filling. After the 3p sublevel, we fill the 4s, and only then do we proceed to fill the 3d orbitals. Second is the Pauli exclusion principle. The Pauli exclusion principle dictates that an atomic orbital can hold a maximum of 2 electrons, and these 2 electrons must have opposite spins, one up and one down. This is often visualized as 2 arrows pointing in opposite directions within a box representing the orbital. Third is Hund's rule. Hund's rule states that for a sublevel with multiple degenerate or same energy orbitals, like the p, d, or f sublevels, electrons will singly occupy each orbital with parallel spins before any orbital is double occupied. For example, to fill the 2p sublevel with 2 electrons, we follow Hund's rule and put 1 electron in each of 2 separate orbitals with the same spin. This is more stable than putting both electrons in the same orbital due to minimized repulsion. Let's apply these rules to write some electron configurations. A full electron configuration lists every occupied orbital. For example, for carbon, which has 6 electrons, we fill the 1s orbital with 2 electrons. Then we fill the 2s orbital with 2 electrons. That leaves 2 electrons for the 2p sublevel. Following Hund's rule, we place 1 electron in each of the first 2 2p orbitals, giving us a full configuration of 1s squared, 2s squared, 2p squared. A condensed configuration replaces the core electrons with the symbol of the nearest preceding noble gas. For carbon, the core configuration is the same as helium's, so we write He2 squared, 2p squared. Now let's consider ions. For anions, or negative ions, we simply add the extra electrons to the lowest available energy level. For example, for a nitride ion, N3, the nitrogen atom has 7 electrons. The N3 ion has gained 3 electrons for a total of 10. This gives it the same electron configuration as the noble gas neon. For cations, or positive ions, it's slightly different. We first write the configuration for the neutral atom, and then remove electrons from the occupied orbital with the highest principal quantum number, n. For transition metals, a common point of confusion is that the 4s electrons are removed before the 3d electrons, even though the 3d electrons fill after the 4s. Let's look at the manganese atom with 25 electrons. Its configuration is argon 4s squared, 3d5. To form the Mn2+ ion, we remove the 2 4s electrons first, resulting in the configuration argon 3d5. While most electron configurations follow the rules, some transition metals exhibit exceptions to the Aufbau principle. The 2 most common exceptions in the D block are chromium and copper. This is because electron configurations that are half-filled or completely filled in the D sublevel are particularly stable. Chromium with 24 electrons might be expected to be argon 4s 2, 3d4. However, to achieve a more stable half-filled 3d sublevel, 1 electron is promoted from the 4s to the 3d, giving it the configuration argon 4s 1, 3d5. Similarly, copper with 29 electrons might be expected to be argon 4s 2, 3d9. But to gain the stability of a completely filled 3d sublevel, 1 electron is promoted from the 4s, resulting in the configuration argon 4s 1, 3d10. These exceptions highlight that the rules we learn are a useful guide, but stability, which is a quantum mechanical effect, ultimately determines the actual electron configuration. Now let's turn our attention to ionization energies and the factors that control them. The first ionization energy is a measure of the energy needed to remove the outermost electron from a mole of gaseous atoms. Because electrons are negatively charged and the nucleus is positively charged, there is an electrostatic attraction. To remove an electron, energy must be supplied to overcome this attraction. Thus, ionization energies are always positive or endothermic. Several factors affect the magnitude of ionization energy. First is nuclear charge. The more protons in the nucleus, the stronger the positive charge, and the stronger the attraction for the electrons. This increases ionization energy. Second is atomic radius. As the outer electrons get further from the nucleus, the electrostatic attraction decreases, making them easier to remove. This lowers ionization energy. Third is the shielding effect. Inner core electrons repel outer valence electrons, effectively reducing the net nuclear charge they experience. This shielding makes valence electrons easier to remove, lowering ionization energy. Fourth and final factor is electron-electron repulsion. This is a subtle but important factor that we'll see explains deviations from the expected trends. All these factors contribute to what we call the effective nuclear charge, or ENC, the net positive charge experienced by an electron. A simple approximation for this is ENC equals nuclear charge minus the number of inner core electrons. The higher the ENC, the higher the ionization energy. Now let's examine the periodic trends in first ionization energy. Across a period from left to right, ionization energy generally increases. This is primarily because atoms are getting smaller and their effective nuclear charge is increasing, holding the outer electrons more tightly. However, the trend is not perfectly smooth. There are two notable dips. The first occurs between group 2 and group 13, for example from beryllium to boron in period 2. Beryllium has its valence electrons in the 2s sublevel. Boron's first valence electron is in the 2p sublevel. The 2p orbital is, on average, further from the nucleus than the 2s orbital and is also slightly shielded by the filled 2s orbital. This weaker attraction makes it easier to remove, so boron's IE is lower than beryllium's. The second dip occurs between group 15 and group 16, for example from nitrogen to oxygen. Nitrogen has 3 electrons in its 2p sublevel, each in a separate orbital with parallel spins as per Hund's rule. This is a very stable half-filled configuration. Oxygen has 4 2p electrons, meaning one of the 2p orbitals must contain a pair of electrons. The repulsion between these two paired electrons makes the 2p4 configuration less stable, so it's easier to remove one of these electrons than it is to remove an electron from nitrogen's stable configuration. The trend down a group is simpler. Ionization energy decreases. This is because atoms get larger, adding a new main energy level each time. The outer electrons are further away, and the increased number of inner core electrons provides significantly more shielding. This outweighs the increase in nuclear charge, weakening the attraction and lowering the ionization energy. Successive ionization energies involve removing more than one electron from an atom. The second ionization energy is always greater than the first, the third greater than the second, and so on. This is because you are removing an electron from an increasingly positive ion, which has a stronger attraction for the remaining electrons. There are also fewer electrons to provide shielding. Successive ionization energy data provides powerful experimental evidence for the electron shell model. If we plot the logarithm of successive ionization energies against the number of electrons removed, we see a gradual increase as we remove electrons from the same shell, followed by a large jump. This jump signifies a change in the main energy level from which the electron is being removed. The large jump occurs when we start removing electrons from an inner shell, closer to the nucleus and with less shielding. By identifying this jump, we can deduce the number of valence electrons and therefore the group of an unknown element. Consider the successive ionization energies of aluminium. We see 3 relatively small increases, followed by a huge jump for the 4th ionization. This indicates that aluminium has 3 valence electrons in its outer shell. Therefore, aluminium is in group 13 of the periodic table. Successive IE data can also provide evidence for sublevel electron pairing. For instance, in argon, there are minor increases between electrons 6 and 7, and between electrons 4, 5, and 6, which can be accounted for by the increased stability of half-filled or filled sublevels and enhanced electron-electron repulsion, similar to the reasons for the dips in first IE trends. Understanding these concepts is crucial for mastering IB chemistry. Let's recap what we've covered. We started by understanding how atomic emission spectra provide experimental evidence for the existence of discrete quantized energy levels within atoms. By analyzing the convergence limit of these spectra, we can calculate ionization energies. We then moved to the quantum mechanical model, defining orbitals and sublevels, and learning the rules that govern how they are filled. The Aufbau principle, the Pauli exclusion principle, and Hund's rule. We saw how to apply these rules to write electron configurations for atoms and ions. Finally, we explored ionization energies, which are a direct consequence of electron configuration. We identified the key factors affecting them and explained the periodic trends, including the dips caused by sublevel energy differences and electron-electron repulsion. We also learned how to use successive ionization energy data to deduce the number of valence electrons and the group of an element. Before we proceed to practice problems, if you're looking for personalized expert guidance to master these and other complex topics in IB, A-Level, or IGCSE chemistry, I invite you to contact DAR Tutors. We provide tailored tuition to help you achieve your academic goals. Now, let's put your knowledge to the test with some IB-style practice questions. I'll show you the question, then pause for you to try it on your own before providing the full solution. Here is our first question. The first ionization energies for the elements in period 2 are shown in this table. Our task is to explain the general increase in IE across the period. Take a moment to pause the video and construct your answer. Welcome back. Here is the solution. From lithium to neon, the nuclear charge increases due to the increasing number of protons in the nucleus. The valence electrons are all in the second main energy level, and electrons in the same shell offer only a small amount of shielding. This leads to a significant increase in the effective nuclear charge experienced by the valence electrons. This stronger net attraction holds the electrons more tightly, making them harder to remove and resulting in a general increase in ionization energy. Our next question asks us to explain the dips in ionization energy at boron and oxygen. Pause the video and think about the electron configurations of these elements. All right, let's go over the explanation. First, for the drop at boron, we compare its configuration, helium-2 squared 2p1, with beryllium's helium-2 squared. The electron being removed from boron is in a 2p orbital, while from beryllium it's in a 2s orbital. Electrons in 2p orbitals are, on average, further from the nucleus and partially shielded by the filled 2s orbital. This makes the 2p electron easier to remove, so boron's ionization energy is lower. Next, the drop at oxygen. We compare oxygen's configuration, helium-2 squared 2p4, with nitrogen's, helium-2 squared 2p3. Nitrogen has a stable, half-filled 2p sublevel, with one electron in each 2p orbital. In oxygen, the additional electron must pair up in one of the 2p orbitals. The electron-electron repulsion within this paired orbital destabilizes the electrons, making one of them easier to remove. This effect outweighs the increase in nuclear charge, resulting in a lower ionization energy for oxygen. Question 3 presents us with successive ionization energies for an unknown element. Our task is to use this data to determine its group number. Look for the largest increase in energy. This will tell you how many electrons are in the outermost shell. Let's work through the solution. To find the jump, we compare each successive ionization energy. The jump from the first to the second is a factor of 2. The jump from the second to the third is a factor of 2. The jump from the third to the fourth is about 1.3 times. But the jump from the fourth to the fifth is a massive factor of 3.7. This very large jump after the fourth ionization energy tells us that the fourth electron was removed from the valence shell, and the fifth electron was removed from a much more tightly held inner shell. Therefore, the element must have had 4 electrons in its outermost shell, placing it in group 14. Question 4 asks for the condensed electron configuration of a titanium ion Ti2+. Remember the special rule for removing electrons from transition metals. Let's find the solution together. First, we write the full configuration for the neutral titanium atom, which has 22 electrons. Following the Aufbau principle, this is 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, 3d2. To get the condensed form, we can replace the first 18 electrons with the symbol for argon. So, the condensed configuration is argon, 4s squared, 3d2. Now for the tricky part. We need to remove 2 electrons to form the Ti2+ ion. From which orbitals do they come? Remember, for transition metals, electrons are always removed from the orbital with the highest principal quantum number first. So, the 2 electrons come from the 4s orbital, not the 3d. The final condensed electron configuration for Ti2+ is simply argon, 3d2. Our final question is another calculation. The absorption of a photon with a wavelength of 486 nanometers excites a hydrogen atom to its second excited state. We need to find the principal quantum number n of this second excited state. Pause and think about what the term second excited state means in terms of the principal quantum number. Let's work through this one. First, let's understand the terms. The ground state is n equals 1. The ground state is n equals 1. The first excited state is n equals 2. The second excited state, which we are looking for, is n equals 3. We are told this wavelength corresponds to the first line of the Balmer series. What is the Balmer series? The Balmer series are transitions that end at the n equals 2 energy level. Since this is an absorption, the electron must have started at n equals 2 and moved up. This corresponds to the first excited state. So, the question is asking what is the final state after the electron from NH2 absorbs the photon? We can use the Rydberg formula to confirm this. While the question doesn't require calculation to find and given the wavelength, understanding the series relationship is key. The first line of the Balmer series involves a transition from N-3 to NH2. Therefore, if an electron absorbs that same wavelength, it must be moving from NO2 to Tn3. The second excited state is indeed NO3. So, by understanding the definition of the Balmer series and excited states, we can deduce that the electron is excited to the second excited state, which corresponds to the principal quantum number and equals 3. That brings us to the end of our session on electron configurations and ionization energies. I hope this detailed explanation and the practice questions have helped solidify your understanding of these crucial IB chemistry HL topics. If you have any further questions, need more practice, or are looking for expert personalized tuition in IB, A-level, or IGCSE chemistry, don't hesitate to contact our tutors. We're here to help you succeed. Thank you for watching.